Well, hello, Seven Blue. Welcome to your second lesson. A little probability today. We've done that quite a bit. It is Thursday, I believe, in your world, although it won't be for anyone who watches this after you. So today we're going to focus on dependent events. We've done these before. We front-loaded it quite a bit. Before we get into dependent events, let's just remind ourselves of independent events. Something like maybe flipping a coin. And if I was to ask, what's the probability of me getting three heads in a row, we should already have the understanding that we know that we take the probability of flipping heads, which is 1 to 2, and then we'd end up multiplying that by the second event, flipping a heads, which anytime you flip a coin, it's always going to be 1 to 2 because it's absolutely independent. And then the third heads, we'd multiply it and call it 1 to 2. Then we'd obviously work that together. That's in the cross cancel. And I would say that the probability is simply 1 to 8. And that's something we've done before. Another thing we've done, but now your official lesson is telling you to do it, is dealt with dependent events. Now remember, let's write this down. When the first event affects the second. So I would think about maybe um, if you were going to a party and you saw that they had laid out all these types of sandwiches like roast beef and turkey and vegetable, whatever, and you're someone who wants the roast beef, and when they call the line, you're like, oh, I hope I get roast beef, and you get like back in the line, and you know the roast beef's very popular, and you see people just grabbing them off the plate. Well, what's happening because they're grabbing the roast beef before you in line is the likelihood of there still being a roast beef sandwich there for you is getting less and less and less likely. And so that's a dependent event. The first event, other people choosing their sandwiches, is affecting your likelihood, the probability that you'll get the sandwich that you like, whether it be roast beef or something else. So we do, whenever discussing kind of events that have that potential, they will usually mark out, look, with replacement, meaning that, well, no one's going to replace the sandwich. But if we were dealing with a deck of cards, which we'll talk about in just a second, are we replacing the card after the first person has chosen? Or, and the second would be without replacement. Now, it's out without replacement that leads us to dependent events. If I don't replace the card, then when I go to the second person and say, hey, grab a card, any card, then it matters what the first person grabbed because things have changed, obviously. Let's talk about that. Now, this structure of how we deal with compound events, events on top of events, such as flipping the coin, is always modeled that the probability of A and B occurring would be the probability of A times the probability of B, which we just did with the flipping of the coin. However, the thing about dependent events is this second event, the probability of B occurring, is gonna probably change. Things have changed if you really think about it. And we'll talk about what has changed. Now, if it's dependent, things have changed. If it's flipping a coin, guess what? Nothing's changed. It's still 1 to 2. However, the reality is we are exploring dependent events. So let's think about like a deck of cards. And if I went to one of you and I said, hey, pick a card and a card, and wondering what the probability of you getting a red is. Now, if I do that to the first person, we'd say the probability is obviously 26 to 52, and we'll reduce that later. Now, as I go to that second person, though, if the first person didn't give me back their red card, and here's the thing, you always assume that the first event occurred, meaning that they got a red card. So no matter what the situation, even if you're like, it's unlikely that they'd get a red card, it's not, but if it was, you still assume that they did. So as I go to that second one, if we think about what is probability built in? It's built in possible outcomes, it's built in favorable outcomes. Now the possible outcomes have shifted from being once 52 without replacement. We're not putting the card back. Now it will be, guess, 51. That's right. Now, another thing that shifted is my favorable outcomes. Because we assume that the person got the red card, it's now shifted from being 26 to, yeah, you can guess it, to 25 because we didn't replace. Now, in order to figure this out, I'm going to reduce the first one from 26 to 52 to simply 1 to 2 because we know that's a reality. And then multiplying straight across, I'd say that the probability of me pulling a red and followed by a second red without replacement would be 25 to 102. And we can box that up. Yeah. Here's another idea we can explore. Please go ahead and write that down. Now remember, if I start talking about something and I start moving ahead and you're not ready, then it might be a good idea for you to um, turn on the heat there. It might be a good idea for you to pause me. You can always pause. I'm going to move on. It says two eighth graders and one seventh grader want to go on the trip. Only two students can go. Seems like a very cruel trip. If two names are drawn randomly, what is the probability that the two eighth graders will be chosen? As I was thinking about this question, I realized one thing for sure about this book, which we'll talk about in a little bit. So we're looking for two eighth graders to be chosen. That doesn't seem very fair, but let's say, in case of the probability of an eighth being chosen by the probability of another eighth. And we would say that the first situation, because there's two eighth graders out of three total, would be 2 to 3. Now remember, because we're obviously not going to put their name back, so we pull out an eighth grader's name and we're like, you're going on the trip. We're not going to put that one back. He's already going. So what has changed? Well, if we think about it, we're clearly not replacement. Therefore, it's dependent. And what has changed is the number of possible outcomes, because now in the hat, there's only two names left. And of those two, only one is an eighth grader, because we know the first one was chosen. Would I cross cancel? You know I would. And I'd end up that the probability of both eighth graders going will be 1 to 3. So I was convinced at the end of this question, they just refer to your book as course 3. And I've always wondered, I'm like, well, is this for eighth graders? Is this for seventh graders? What is it? I'm pretty sure we can move forward and say that unquestionably that the textbook you use is designed kind of for eighth graders. Yeah, because they wouldn't create a question like this that would make the entire room feel like that's not fair. Why don't the seventh graders get to go? Hey, we got another one. Let's do it. A bag containing marbles. We've all seen it, or at least we've seen it hundreds of times in our Saxon books. Maybe we don't even know what a marble is, but then I'd say, well, you're not paying attention to Christmas time. So a bag contains 2 white and 3 blue marbles. What is the probability that 2 blues will be chosen from 2 picks? So we're just going to go in that marble bag twice. Now, we're going to first consider it with replacement. So with replacement would be, so it's probability a blue followed by a blue. Now with replacement means one thing only. It means independent. Nothing about the first choice matters because what's going to happen, and we know what's going to happen, is that I'm going to grab the blue. There are 3 of them out of 5, so that's 3 to 5. Now I'm going to, the kid who got the blue, I say, okay, put it back in the bag. And I go to a second kid, well, guess what? It's still 3 to 5. And this is an independent event. And I would multiply straight across and I'd say, oh, the probability is 9 to 25 and box that up. Now, without replacement, now that's going to lead us to our dependent situation. So the probability of blue followed by a blue, first event is clearly 3 to 5. Now, the second event, though, is what has changed because um, what has changed is both possible outcomes from 5 to now 4, and also favorable because we assume that they chose the blue. We must assume that. So the 3 has become a 2. And then I would cross cancel this and I'd end up with 3 to 10. Yeah. So here's a question for you, just a little bonus question. Which is more likely to occur, the 9 to 25 or the 3 to 10? You've got 1, 2, 3 to answer. It's the 9 to 25 is more likely to occur. Yeah. Hey, that's our lesson. This one's a lot shorter. And I'm just really happy about yesterday's lesson. That's one of the biggies. You know, we graph a lot next year. So I'm glad we kind of got that under our belt. Another way to graph equations. And also just that little snapshot into systems. Very exciting. Systems, there's actually 3 ways that we will solve those as we move forward in life. But you learned one of them yesterday, solving through graphing. And hopefully your graph looked a lot better than mine, and it should have been dropping exactly at 5, -2. That was the goal. Other than that, that does close this lesson. So just as a reminder, this lesson was lesson 83. You are expected to do homework 83. Hope all is well. If you're having any issues at all, you can reach out to me. Take care. Bye-bye.